My name is Tegowski, and I'm from the Institute of High Frequency Technology at the Hamburg University of Technology. In this video of the series What's Hot in Antennas and Propagation, I would like to give a short overview on our article Near Field Scattering Phenomena and Monostatic Radar Applications Derived from Physical Optics, which is published in the IEEE Transactions on Antennas and Propagation. The well-known principle to characterize scattering for radar applications is given by the concept of the radar cross-section, short RCS. It derives from the power density ratio of the scattered and incident plane waves. For this, one assumes that the range R is significantly larger than the target size D, such that the antennas are located in the target far field. That means the far field distance defined by the size of the target. However, this condition is not satisfied in every application. And this is what we investigate in this article. We analyze what happens if the range reduces such that the target size becomes comparable to the range. Here the relationships are a little bit more complicated because of the inhomogeneous elimination by the transmit antenna and because the receive antenna receives scattering contributions from different directions. To describe scattering in such a target near-field environment, we introduce the radar channel transfer function. It is given by the ratio of the power wave A that feeds the antenna and the power wave B that is received in the antenna terminal. In the article, we focus on a monostatic setup and derive this definite integral, which predicts the radar channel transfer function in the near field of an electrically large target, in terms of both magnitude as well as phase. The derivation is based on combining physical optics principles and the antenna radiation pattern. To investigate the near-field scattering phenomena, we consider this representative setup here with circular disks as targets. We simulate and measure the radar channel transfer function for different target sizes, different antennas, as well as frequencies. And what are the results? Well, first in terms of magnitude. For a small target, one obtains a magnitude response over distance as expected from far-field relationships. But now the interesting question is, will these curves just be shifted to higher power levels for the larger targets according to their larger radar cross-section? No, this is not what happens. One observes power fading phenomena which lead to local maxima and minima. Their prominence depends on the antenna directivity. And what is the effect on phase? In the target's near field, the phase suffers from nonlinear distortion relative to its linear far-field dependence. So if the radar antenna is in the target near field, a very interesting scattering phenomena results. These can be well predicted by the proposed radar channel transfer function. If you're interested in more explanations, follow the QR code which brings you directly to IEEE Explore, where you can find the article in its full length. In this article, we discuss the near-field scattering effects in general for a monostatic setup in a simple target. But there's more to come, so don't forget to check out our current and future works. Thank you very much for watching and your interest.